Bond energy or bond enthalpy. Remember this, that bond formation is exothermic and bond fission is endothermic. So in both cases, energy is concerned. So the energy released when 1 mole of bond is formed, or the energy absorbed when 1 mole of bond is broken down, is known as bond energy. For example, if 1 mole of hydrogen atom reacts with 1 mole of hydrogen atom, producing 1 mole of hydrogen molecule, then a total amount of energy 435 kilojoule per mole energy is released because of having negative sign, because the bond is formed here, so the process is exothermic. While if you want to break the same 1 mole of hydrogen bond to produce 2 mole of hydrogen atoms, then the same amount of energy is absorbed with a positive sign 435 kilojoule per mole. Factors affecting bond energy, and these are the main concept by which various questions can be devised to present for you. Change in electronegativity is directly proportional to bond energy. If the change in electronegativity of the two bonded atom is higher, then bond energy will be higher. For example, if you look, HF has higher bond energy than HCl. It has higher bond energy than HBr, and HBr has higher bond energy than HI. The reason is that in HF the electronegativity difference is higher. While going down the group the electronegativity decreases, so in case of hydrogen iodide the electronegativity difference is smaller and the bond energy is also low. So change in electronegativity directly proportional to bond energy. The second factor is bond length is inversely proportional to bond energy, means shorter bonds have high bond energy and longer bonds have low bond energy. For example, carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bond. Their lengths are: carbon single bond is 1.54 angstrom, carbon double bond is 1.34 angstrom, and carbon triple bond is 1.19 angstrom. Now look at their bond energy. If you want to break carbon-carbon single bond, you need 348 kilojoule per mole energy, while in double bond this amount increases 614 kilojoule, and while in triple bond it further increases up to 839 kilojoule per mole. This shows that a shorter bond has a high bond energy like carbon-carbon triple bond, and a longer bond has a low bond energy like carbon-carbon single bond. Similarly, oxygen-oxygen single bond is longer, so it has 146 kilojoule per mole of bond energy, while oxygen double bond oxygen is shorter, it has 495 kilojoule per mole of energy. The next factor is atomic size is inversely related to bond energy. If we have smaller atoms, the bond energy will be higher, and if we have larger atom, the bond energy will be low. For example, carbon single bond carbon, it has the bond energy of 348 kilojoule per mole, while in silicon single bond silicon, it is a bond energy of 2 to 6 kilojoule per mole. The reason is that carbon is the top of the group. These are of smaller size, and silicon are of larger size. This is why the bond energy of silicon single bond silicon is smaller compared to the bond energy of carbon to carbon single bond, because carbon has smaller size, higher bond energy, silicon has larger size and low bond energy. There are some abnormalities in this trend, and remember these. In halogens, chlorine has higher bond energy than bromine, bromine higher than fluorine, and fluorine higher than iodine. Though fluorine is the first member having a smaller size, it should be expected to have high bond energy, but its bond energy decreased. This is another phenomena, but remember here this abnormal behavior in halogen as well as in group 6 oxygen family. There is this abnormal behavior, to remember this. Another factor is hybridization. sp3 hybrid bond has less bond energy than sp2 hybrid bond, and sp2 hybrid overlapping less than sp hybrid bond. Why? Because in sp3 we have percent of s character 25%, while in sp2 it is 33.3%, and in sp it is 50%. This shows that percent as character is directly proportional to bond energy. Polarity. Polar covalent bonds have high bond energy than non-polar covalent bond. For example, non-polar bond of hydrogen-hydrogen and a non-polar bond of chlorine-chlorine. These two bonds have lowest energy than a polar bond between hydrogen and chlorine, because here a polar bond is formed, due to which electronegativity difference arises and bond energy increases. Here both the bonds in hydrogen-hydrogen and chlorine-chlorine are non-polar. They have zero electronegativity difference, so their bond energy are low compared to HCl.